Test. Hi, I'm Jason, and Jason Lee from CMU. I got my PhD from CMU, and I'll be talking about preconditioning and locality algorithm design. So in this talk, we'll be considering a bunch of fundamental classic graph problems. For example, graph cut problems like min cut, and actually all types of variants of min cut problems. And also some special graph theory problems like conductance and expanders. And also, we'll briefly look at some graph distance problems like shortest path. Of course, shortest path is easy in sequentially. So we're looking at shortest path in parallel and problems of similar flavor. And the two techniques we'll be using to attack these problems are preconditioning and locality. So preconditioning, let's first begin with preconditioning. So preconditioning has its roots in numerical linear algebra, where it's the common technique is to precondition a matrix in some linear system. But in the context of graph algorithms, I like to think of preconditioning as a distinction between worst case and average case. So preconditioning is the technique is about preconditioning a general case problem, a worst case problem, to behave like an average case problem. So that kind of allows us to kind of assume that the input is random. And of course, random inputs are just random. We want to kind of exploit some kind of structure from them. And the structure that we want to exploit depends on the problem context, of course. So for graph cut problems, we'll be exploiting the fact that random graphs are expanders. And for distance problems, we'll be using that random graphs have low aspect ratio. And of course, once we solve the random problem, we want to reduce general instances to random instances. And here, for the graph cut problems, one common technique we use is expander decomposition. This is decomposing general graph into expanders by deleting a small number of edges in between. These red edges in between is a small fraction of edges. And historically, this concept of preconditioning in the context of graph algorithms was popularized by Spielman and Tang in their seminal result on solving the quadrant systems quickly. That's it for preconditioning. And for locality, so locality has its roots in local algorithms, local graph algorithms. And these are algorithms which begin with some seed vertex V and just explore a small neighborhood around V. So in particular, the running time of a local algorithm is much smaller than the entire graph. So it does not look at the entire graph. So typically, a good local algorithm will run in time proportional to the smaller side of some cut it wants to find. In particular, it's like sublinear in the input size. And one famous example of a local algorithm is PageRank nibble, which computes approximate conductance. In this talk, we'll be looking at locality not from this local algorithm model, but as a fundamental principle in algorithm design. So how can we use locality, exploit locality to obtain faster algorithms in the classical setting? So we'll be thinking of locality as a distinction between unbalanced cases and balanced cases. So whereas preconditioning, we assume that the input graph is random, in the locality case, we assume that the target solution is local to some vertex. In particular, suppose the target solution is a graph cut. We're assuming that the graph cut is local to some vertex V that we may or may not know. And of course, once again, it's not enough to just assume unbalanced. We want to reduce general instances to unbalanced. And our techniques depend on the problem. Sometimes we can obtain a straight reduction, and sometimes you have to handle the balance case separately and exploit additional structure from the balance case. These are two problems. And okay, so for the remainder of this talk, I want to kind of make a case for these two problems, to these two techniques. In other words, why these techniques are cool and why we should care about them. So for one, I claim that these techniques are powerful. They have made progress on these classic graph cut and distance problems. For example, it has led to the current fastest algorithms for example, various min cut problems, parallel shortest path, also like deterministic expander decomposition, which itself was used for deterministic preconditioning and so on. It's also versatile. It applies to all types of graph problems. For example, in the particular case of min cut, we were able to apply for practically every single variant of min cut that we studied. And finally, I want to claim it's cutting edge, no pun intended. That, in other words, these techniques have mostly been unexplored in the past, which is significant because that concerns future potential. In other words, these techniques have a lot of future room to grow and develop. And this will be the hardest claim to make. And for the rest of the talk, I want to kind of like give a feel of how simple these results are. How simple some of these algorithms are, these state-of-the-art algorithms. And that's significant because a simple algorithm that has remained undiscovered for so long is usually a sign that what we lacked in the past was not the right technical tools, but the right perspective. So this is a matter of perspective, not developing like concrete technical tools. Okay, so the problem we'll be considering for the rest of the talk is Steiner min cut. And this is it's a simple generalization of like, say, global min cut or ST min cut. Given a graph and a subset of vertices called terminals, find the min cut that separates at least two terminals. So for example, if the set R is just S and T, is ST min cut. If the set R is all the vertices, it's global min cut. And historically, this problem has been studied in the context of Gomery-Hu tree, which or in other words, all pairs min cut. And the fastest algorithm is one running in time n plus nc squared, where c is the size of the target min cut, the Steiner min cut. So to solve this problem, we're making it almost like a leap of faith. We'll be assuming that the Steiner min cut is unbalanced, but in fact so unbalanced that there's only one terminal on one side. So this blue cut here has only one terminal on this side. Now, of course, at first glance, this assumption does not seem to be that fruitful of an assumption. Like why do unbalanced cuts capture the general case? And also what can we gain from assuming such an assumption? And in fact, like when I started working on this problem, I had no idea either. All I knew was that locality was a useful concept. It's been successful in the past. Let's just try it here. And that turned out to be this key assumption turned out to be the key step in the entire algorithm. After we assumed this, everything else almost came together immediately. So in particular, why is this general enough? Turns out you can reduce general cases to this unbalanced case by random sampling. And we'll see this later. It's very simple. Okay, so the theorem I want to cover in the last like 3 or so minutes is that, well, first of all, the unbalanced Steiner min cut can be solved in polylog max flows. So this requires, for this we define a new problem that essentially captures the unbalanced case. And we essentially gave a simple algorithm to solve this problem in log and max flows. And then in general, for the general case, we reduced the general case to the unbalanced case by simple random sampling. So first, let's go over the unbalanced case. So here, essentially, the problem we want to consider is this minimum isolating cut problem, which is given the graph in the terminals, find for each terminal the min cut that separates that terminal. Essentially, we know the cut is unbalanced. We don't know which terminal is on the unbalanced side, so we just try them all. This is essentially the problem. And trivially, it will take R min cuts, the size of R min cuts, SD min cuts to solve. But we show a very simple algorithm that uses log R SD min cuts. And this algorithm is actually very simple. If I had 5 more minutes, I would have shown it and proved it. It's like 2 pages long in the paper. And it implies an unbalanced Steiner min cut. And finally, how do we reduce general Steiner min cut to unbalanced? Well, it turns out we just need to random sample at an appropriate sampling scale. So if we sample at rate, let's say 1 over the size of S intersect R, the number of terminals in the let's say the smaller side of the target min cut, then with constant probability, we'll sample exactly 1. And we'll just call this minimum isolating cut the unbalanced case on the subsample and get the right answer. And of course, we don't know which scale to sample, but we can just sample at like geometrically increasing scales. So as a recap, what happened was we assumed this locality assumption that the standard min cut is unbalanced, one term on one side. We formulated a problem and that captured that instance and solved it. And then finally, we established simple reduction from general standard min cut to this unbalanced case by random sampling. In terms of this standard min cut, this simple algorithm is state of the art. Previously, nothing was known even in like sublinear in R max fields. So nothing non-trivial was known in the general case for standard min cut. So finally, last slide, what about de-randomization? So what if we want to de-randomize that random sampling step in the standard min cut? So it turns out here, it's not so clear how to de-randomize in general, but what we're going to exploit is that if G is an expander, now I have to, it's a bit more technical to define what it means to be expanded with respect to a subset R, but let's just forget about that for the talk. If G is some sort of expander, then the standard min cut is guaranteed to have a small number of vertices on one side. And the intuition is basically if the sign wasn't balanced, then it automatically becomes a low conductance cut and it cannot be an expander contradiction. That's the intuitive claim. And it turns out that unbalanced case, in this case, it means like not one vertex, but like some polylog number of vertices on the smaller side. That's easy to randomize. This is standard de-randomization tools. And finally, to get the general case, we precondition the graph by expanded decomposition. So that essentially, we only need to solve the expanded case. So essentially, this determinate standard min cut problem required both locality and preconditioning to solve. But that's it for my talk. Again, this is the list of problems I've looked at so far, and yeah, thanks for listening.